Schottky specific heat anomaly. Consider a system which consists of capital N weakly interacting particles, and suppose that each of these can be in either one of two states with respective energies epsilon 1 and epsilon 2, epsilon 1 less than epsilon 2. Without explicit calculation, make a qualitative plot of the mean energy of the system as a function of its absolute temperature. So we're going to plot E bar versus T for a system that has capital N particles. Each particle has energy epsilon 1, where epsilon 1 is less than epsilon 2. And we're also going to use this plot to make a qualitative plot of the heat capacity of this system. So C versus temperature, assuming all external parameters remain fixed. Show that this plot exhibits a maximum and estimate roughly the value of the temperature at which this maximum occurs. So the critical temperature for maximum point. That's what we're going to find out. Calculate explicitly the mean energy and heat capacity as a function of temperature of this system. Verify that your expressions exhibit the qualitative features described in part A. So here we're going to do a verification by explicit calculation. Cases where two discrete energy levels of a system become important in a given temperature range do occur in practice. The accompanying heat capacity behavior is called Schottky anomaly. So let's start with recalling the result from problem 4.8. So as temperature goes to 0, we're going to have a ground state in the system. So the minimum energy, E minimum, will correspond to all particles residing in the ground state, capital N times epsilon 1. And as t goes to infinity, we will have a random distribution of particles, which will give us the energy capital N epsilon 1 epsilon 2 divided by 2. So this was the result of problem 4.8. So if we plot this mean energy as a function of temperature, we have a transition between two limits, capital N epsilon 1 and capital N epsilon 1 plus epsilon 2 divided by 2. And this transition occurs at a critical temperature where KTC is the difference in the energy levels, epsilon 2 minus epsilon 1. So Tc is approximately epsilon 2 minus epsilon 1 divided by K. So we can approximate it this way. And if I show you the energy levels here, this is the energy level diagram, epsilon 1, epsilon 2, and the energy difference delta E. And when this delta E is comparable to KT, we have significant excitations to the higher energy level. So that's why we have this critical temperature Tc. So this all these results come from problem 4.8. Now, if I go to heat capacity, all I have to do is remember that heat capacity is equal to the derivative del epsilon bar del T with all other external parameters fixed. So all I need to look at is the derivative of this function. So here I can note that there is zero slope. Here I have zero slope. Here I have positive slope. Here I have negative slope. So if I were to put a line here that goes through any of these points, I would see that this line would have a positive slope. And on this side, when I put a line here, for example here, I would find that this line has a negative slope. So first it's an increasing and then it's a decreasing rate of increase in the E bar as a function of temperature. So I can plot qualitatively what will happen to heat capacity as a function of temperature based on this observation. So my qualitative plot will look like this. Heat capacity is a function of temperature. For low temperatures, I have zero slope. For high temperatures, I have zero slope. And in the middle, I have first a positive slope, an increasing positive slope, and then I have a decreasing slope as a function of temperature. And this maximum will occur roughly at this critical temperature Tc, where I have the transition between these two behaviors. Now, let's do this explicitly in part B. Now we're going to do an explicit calculation of the mean energy as a function of temperature and heat capacity as a function of temperature. So let's start with mean energy per particle. So epsilon bar will be given by the canonical distribution because we have one particle interacting with the rest of the particles. The mean energy is calculated by multiplying the energy with its corresponding Boltzmann factor, e to the minus beta epsilon 1, and add to it epsilon 2 e to the minus beta epsilon 2 divided by the partition function e to the minus beta epsilon 1 plus e to the minus beta epsilon 2. So this will be equal to, if I take this into epsilon 1 parentheses, I'm going to have epsilon 1 e to the minus beta epsilon 1 parentheses. I will have a 1 here plus epsilon 2 divided by epsilon 1 e to the minus beta epsilon 2 minus epsilon 1, and here I have e to the minus beta epsilon 1. And I do the same thing for the bottom. I have 1 plus e to the minus beta epsilon 2 minus epsilon 1, and here I have e to the minus beta epsilon 1. So these two will disappear, and I will be left with this expression. And how do I calculate the mean energy of the whole system? It's going to be equal to capital N times epsilon bar. So the mean energy E bar will be equal to capital N epsilon 1 times 1 plus epsilon 2 divided by epsilon 1 e to the minus beta epsilon 2 minus epsilon 1 divided by 1 plus e to the minus beta epsilon 2 minus epsilon 1. And on the other hand, the heat capacity is the derivative del E bar del T, which is capital N times del epsilon bar del T. the epsilon bar is a function of beta, so it's going to be capital N del epsilon bar del beta del t. So this becomes capital N epsilon 1 del beta del t multiplied with the derivative with respect to beta of the quantity in parentheses, the expression in parentheses, 1 plus epsilon 2 divided by epsilon 1 e to the minus beta epsilon 2 minus epsilon 1 divided by 1 plus e to the minus beta epsilon 2 minus epsilon 1. So we can continue this calculation from here. So what I'm going to do for this is take the derivative of beta with respect to t. Now I remember that beta was defined as 1 over kt. So the derivative of beta with respect to t is minus 1 over kt squared. So I can substitute that here. So for the heat capacity, I will have capital N epsilon 1 minus 1 over kt squared. That's the derivative of beta with respect to t. And now I can take the derivative of the top, multiply it by the bottom, minus the derivative of the bottom, multiplied by the top, divided by bottom squared. That's the division rule for the derivative. So if I take the derivative of the top, the derivative of 1 is going to give me 0. Then I will have epsilon 2 over epsilon 1. So first I will have epsilon 2 over epsilon 1. The derivative of e to the minus beta epsilon 2 minus epsilon 1 will give me, with respect to beta, minus epsilon 2 minus epsilon 1. So I need a minus sign here. I will get epsilon 2 minus epsilon 1 multiplied by the exponential e to the minus beta epsilon 2 minus epsilon 1, and this has to be multiplied with the bottom, so 1 plus e to the minus beta epsilon 2 minus epsilon 1, and then I have to take the derivative of the bottom with respect to beta, so that will give me a minus beta epsilon 2 minus epsilon 1 times the exponential. But since I have a minus sign, so derivative of the top multiplied by the bottom minus the derivative of the bottom. So minus the derivative of the bottom will give me a plus sign here. Plus epsilon 2 minus epsilon 1 e to the minus beta epsilon 2 minus epsilon 1. That is multiplied with the top, which is our 1 plus epsilon 2 over epsilon 1 e to the minus beta epsilon 2 minus epsilon 1. And this has to be divided by the bottom square, so I have 1 plus e to the minus beta epsilon 2 minus epsilon 1 parentheses squared. Now I'm going to take this into epsilon 2 so let's take a look at what happens here. I have epsilon 2 minus epsilon 1 e to the minus beta epsilon 2 minus epsilon 1 appearing on both expressions here. So I'm going to take that into these parentheses. So I have minus capital N epsilon 1 over kt squared. Then I have epsilon 2 minus epsilon 1 e to the minus beta epsilon 2 minus epsilon 1. Then I have in parentheses minus epsilon 2 divided by epsilon 1 multiplied with 1 plus e to the minus beta epsilon 2 minus epsilon 1. And then in the second term, I have 1 plus epsilon 2 over epsilon 1 e to the minus beta epsilon 2 minus epsilon 1. And this is going to be divided by the denominator squared 1 plus e to the minus beta epsilon 2 minus epsilon 1 squared. And now if I continue my calculation here, so in the numerator part, I see that I will have minus epsilon 2 over epsilon 1 minus epsilon 2 over epsilon 1 exponential. So here I have 1 plus epsilon 2 over epsilon 1 exponential. So I see that this part will disappear with this part. So combined with that part. So I will be left with 1 minus epsilon 2 over epsilon 1 in the numerator. So this is going to be minus capital N epsilon 1 divided by kt squared. I have epsilon 2 minus epsilon 1 e to the minus beta epsilon 2 minus epsilon 1, and then here I have 1 minus epsilon 2 over epsilon 1 divided by 1 plus e to the minus beta epsilon 2 minus epsilon 1 squared. So this will give me, if I operate the minus sign into this epsilon 1 minus epsilon 2 over epsilon 1 term, so this would be capital N epsilon 1 over kt squared. I'm taking care of this minus sign. There is epsilon 2 minus epsilon 1 here. There is the exponential here, e to the minus beta epsilon 2 minus epsilon 1. And this term, instead of becoming epsilon 1 minus epsilon 2, will become epsilon 2 minus epsilon 1 divided by epsilon 1. And then I have the whole thing divided by 1 plus e to the minus beta epsilon 2 minus epsilon 1 squared. And here I can see that this epsilon 1 will get rid of this epsilon 1, and I will have epsilon 2 minus epsilon 1 squared. And instead of 1 over kt squared, so let me multiply this by kt and divide it by, multiplied by k and divided by k, so that I can write the heat capacity as capital NK beta squared. Beta squared is 1 over k squared t squared. Capital NK epsilon 2 minus epsilon 1 squared e to the minus beta epsilon 2 minus epsilon 1 divided by 1 plus e to the minus beta epsilon 2 minus epsilon 1 squared. So this is the explicit expression for heat capacity as a function of temperature. And on the other hand, here I have the explicit expression for the mean energy as a function of temperature. Now I can look at the limits and see if I get the behavior that I expect. So as the temperature goes to 0, so at this point I'm looking at the limits. So first, let's look at what happens as temperature goes to 0. I'm going to define alpha as epsilon 2 minus epsilon 1. So, and remember epsilon 2 is greater than epsilon 1, which is a positive quantity. So as temperature goes to 0, beta, which is 1 over kT, goes to infinity. And what happens to e to the minus beta alpha? E to the minus infinity, which is going to 0. So if I look at the heat capacity expression, so what will happen to heat capacity? I have a beta squared, and then I have e to the minus beta alpha term, this e to the minus beta epsilon 2 minus epsilon 1. Then at the bottom I have 1 plus e to the minus beta alpha squared. So that's the behavior. And because e to the minus beta alpha is going to 0, e to the minus beta alpha is much less than 1, I can neglect this one. So that's going to be, basically the behavior is beta square e to the minus beta alpha. So my goal here is to determine what happens to heat capacity in this limit. So let me look at the limit as beta goes to infinity. What happens to beta square e to the minus beta alpha? Using L'Hopital's rule, I can first write this as beta goes to infinity. This is the ratio e to the minus beta alpha beta square divided by e to the beta alpha. And you can see that this is an infinite over infinite problem. So I can take the first derivative limit as beta goes to infinity 2 beta alpha e to the beta alpha. That is still infinite over infinite. Another derivative, the limit as beta goes to infinity 2 divided by alpha square e to the beta alpha. And now that is a constant divided by infinite, which is 0. So I find that therefore I find that as beta goes to infinity, t goes to 0, heat capacity goes to 0 as expected. And this is also consistent with the third law of thermodynamics, if you remember. Now I'm going to look at another limit. What happens as temperature goes to infinity? Then beta will go to 0, and e to the minus beta alpha will become 1. So the heat capacity then will become beta square nk epsilon 2 minus epsilon 1 square e to the minus beta alpha will be 1 divided by 1 plus 1, 2 square, which is 4. Now as beta goes to 0, you can see that this is going to go to 0. Therefore I find that the behavior is indeed the heat capacity becomes 0 in these two limits. Now on the other hand, I want to look at what is happening to the heat capacity as I go to the limit t goes to 0 functionally by looking at its derivative. So also as t goes to 0 or beta goes to infinity, I can see that I have this behavior. It is beta square e to the minus beta alpha and if I take the derivative with respect to temperature of this would be del C del beta del t. So I will have minus 1 over kt squared multiplied with del c del beta. So it will give me 2 beta e to the minus beta alpha. And then the second term, it will give me a minus alpha multiplied with beta square e to the minus beta alpha. And if I multiply the top and bottom with k, I will basically obtain for this derivative minus k over k squared t squared. So it's minus beta square k times 2 beta e to the minus beta alpha, and then I have minus alpha beta square e to the minus beta alpha. So e to the minus beta alpha is approaching 0 here as beta goes to infinity, and therefore if you look at this expression in e to the minus beta alpha parentheses minus beta square k e to the minus beta alpha, then I have 2 minus two k so it's minus beta square k e to the minus beta alpha 2 beta, and I can take that beta out too, so this would be 2 beta cube. So 2 minus alpha beta that is remaining here. And because I have the minus sign here, I can make this plus, I can make this minus and make this plus. And alpha times beta is much greater than this 2, so alpha is a constant, but beta is going to infinity, so this side can be ignored. So you can see that I have beta cube k e to the minus beta alpha, alpha k beta, which is positive. So I can see that the derivative del c del t is positive as t goes to 0. On the other hand, I can look at the derivative as t goes to infinity. As t goes to infinity or beta goes to 0, if you look at what happened as t goes to infinity and beta goes to 0, I had c proportional to beta square. So what happens to del c del t in this range? Because I have del c del beta del t, this is going to become del c del beta multiplied by minus 1 over kt squared. That is the derivative of this. And in this limit I had a c proportional to beta square, so it's going to give me del c del beta will give me a factor of 2 beta. So it will go as 2 beta minus 1 over kt square. If I multiply the top and bottom with k, this will be minus k beta square, so it's going to be 2 beta cube. Now beta is going to 0, but beta is positive, so this has a minus sign here, so it is going to be negative. So del c del t is negative as t goes to infinity. So this basically tells me that the c as a function of t curve will look like this, First it is 0, then it has a positive slope, then it has a negative slope, and it goes to 0 again. And this happens at this critical temperature Tc. So indeed the verification has been completed. The behavior is as expected. We see a positive slope at the beginning and a negative slope later on when we approach t is equal to infinite limit. So we started out with a system that has two energy levels, epsilon 1 and epsilon 2. The energy difference is delta E. As t goes to 0, we have the minimum possible energy ground state configuration, capital N epsilon 1. As t goes to infinity, we have the most random distribution, capital N epsilon 1 plus epsilon 2 over 2 will be the mean energy. And the critical temperature corresponds to the significant transitions when the thermal energy matches the energy difference between these two levels. And if you look at the derivative of this, this is going to be a symmetric peak here at approximately this critical temperature Tc. And in the explicit calculation, first I calculated the mean energy per particle, then I multiply it by capital N to find the total mean energy. Then I take the derivative with respect to temperature and find that the behavior is beta square e to the minus beta alpha divided by 1 plus e to the minus beta alpha parentheses squared. So we see that as t goes to 0, c goes to 0 here, as t goes to infinity, c goes to 0. And I also check the derivative. It is positive when I approach t equals to 0, and it is negative when I approach t is equal to infinity. So indeed this suggests that the behavior, as we see on this plot, is that of a sharp peak occurring at t is equal to Tc, and this behavior is known as Schottky anomaly.